We now move on to section 1.5. We are now interested in, let me just use it slightly. Okay, this looks much better. Okay, section 1.5. Sorry, so this is the section about cardinality. And I said, we're not going to stop at every single point here. We're just going to focus on the essentials. This is not really that important, but it highlights one application at least of what's referred to here as the axiom of completeness over the fact that all bounded sets in real numbers have a supremum. So what makes them complete? What makes the real numbers complete? Okay, so now we are going to we're going to now see what this new notion of cardinality means. And basically, so this is an idea that Cantor, this is the whole theory that Cantor developed, which incidentally was an idea that he said came to him. I don't know how reliable these accounts are, but came to him from above, and so that's what he was instructed to communicate, the theory of transfinite numbers to all us mortals. But in any case, the theory is very beautiful and everything, but it doesn't seem to have, much applications nowadays to analysis. Of course, it has influence questions in logic and general topology and stuff like that, but it's not going to be that relevant for us. So the thing is that, so what is this notion of cardinality? Well, for usual sets, that cardinality just means the number of elements there are in the set. So you have a way of, you have an easy way of knowing for finite sets which sets are larger than others by simply counting their elements. So the elements, if one set has more elements than another, then you think of it as being bigger. And of course, two sets are going to be equally big if they have the same number of elements. So in that case, they have the same cardinality. Cardinality is a way of counting the way it's thought of when you have finite sets, it's just you count the number of elements. So here, so here this is the set A, this is the set B, and instead we have triangles. And the way to determine whether two sets have the same cardinality is just to count the elements in each one. In this case, we have 1, 2, 3, 4, 5. Cardinality of the set A is 5. And here we have 5 triangles. So the cardinality of B is equal to 5. So then we can, after we've counted the number of elements, we can say that A has the same cardinality as B. So, but this, this notion here of cardinality hinges upon the ability to count. So So everything here depends on being able to count the number of elements. So what if you wanted to compare the size of two sets with infinitely many elements? Well, you say, okay, but they both have infinitely many elements, so they're gonna have the same cardinality automatically? Well, there are sets that even though you may think, oh, they're both infinite, there's sets that are much larger in a notion that will become clear now. That is the right notion for cardinality. Here, remember, if two finite sets have the same number of elements, like here, so if you can count them, then it is clear you can deduce whether they have the same cardinality or not. So is there a notion? Is there a notion that allows to compare the sizes of infinite sets? So is it possible or not? The notion allows to compare the sizes of infinite sets. Well, you cannot rely, of course, on counting the number of elements because then you will be stuck. I mean, you will count infinity and you would say, okay, then this should be the same. So in order to answer this question, it's better to think about how can you compare the two sets directly without counting anything. So one way of doing that is realizing if they both, I mean, using the fact they already, I mean, you're going to use the fact that they both have the same cardinality in terms of this number of elements to come up with a notion that will allow you to forget that you counted the elements and therefore allow for your construction. So what's the idea? Here is have the same number of elements, and you can assign to each one of the elements in the set A one element in the set B and only one. There's going to be one. Sorry. It's going to be only one element assigned to each element in the other set. Right? So we cannot even erase. So this is the idea. There must be a one-to-one correspondence between each element in A, I mean between elements in A and elements in B. Because then, I mean, of course, you know, if you can assign one element, only one element of B to each one of the elements in A, then when you count, counting elements in A will be the same as counting elements in B. Because if you count one element here, like this one, you might as well have been counting this one, and then you pass to the second one and the same. So if there is such a relationship between the two sets, then you can definitely say that at least in the finite case you have the same, I mean the two sets have the same number of elements. But what is it, this relation? You think about it, I mean, I used arrows. I mean, in this sort of picture, using Venn diagrams should be reminiscent to you to some other notion in mathematics. that we use basically for everything is the notion of function. So this is a map F going from the set A to the set B, and we will have properties. So the properties of F that we want are the following. So remember that this is just a map. So a function from A of F, there's a function that goes from A to B. Okay. First of all, if you want to count the same number of elements in A, the same number of elements in B, well, first of all, F has to be a function. To each element in A, there must be an element in B that F maps to. Also, you need the property that no two points in A are mapped to the same element in B. If that is the case, then you would not be counting the same number of elements. Think about the extreme case where you let all the points be mapped onto only one point in B. Then you'll be counting one point on one side, where you're counting a much larger number in A. So you want to have this property, which means that F is 1-to-1 or is injective. So the first one is F is injectivity 1-to-1. Or injective. And what does this mean in terms of actual mathematics? You can write it in two ways, and they're both correct. This is injective function. One is which means that for every x different from y, both elements in A, because F is only defined there, so you're just gonna skip that part. X is different from y. F of x is different from f of y. Or this, if x different from y implies that f of x is different from f of y. And this is the same as saying that if you have point x and y such that their images are the same, then the points must be the same. Okay, so that is what this property here says. If you start from different points, then you're going to land in different points. If you apply the map F, or if you happen to see that two images of points x and y are the same, that means that the 2 points were actually the same point to begin with. And the other one is, if you want to count the same, maybe you have this property of injectivity. For instance, if you have like one set over here, and you have again my triangles, and you're assigning only one triangle to each point, but then there's going to be something here missing. So the number of points here is going to be smaller than the number here. The number of points is going to be smaller than the number of points here on the right hand side, on the right side. And the other one is, but F is surjective. What does this mean? In mathematical terms, it means that for every y in B, there exists an x in A such that f of x is equal to y. No matter what element you pick in B, you're going to be able to find an element in A such that f of x is going to be equal to y. An element x in A such that f of x is equal to y. And so these two properties, I mean, if we find a function like this, you know that when you count elements on one side, will give you the same number if you count elements in the other set. So if we have a function from A to B, and we have a function with these two properties, then when you count the numbers in A, you're going to obtain the same thing as if you count the number in B, because it's a one-to-one correspondence. It's basically just changing labels. This is gonna, so you have numbers 1 to 5, and you have 5 balls. It's just putting on a label in each one of the balls, and that will give you the same number. When you have 5 balls and you have number 1 to 5, you can put a label to each one of these balls, and you basically count the 5 balls because each one has a label in it. And labels are not repeated. This means that the function is injective, and it's surjective, so all the balls have a label. Okay, so every ball, I mean, no ball has two labels. Means that it's one-to-one, and every ball has a label. So the map is surjective. So counting the number of balls becomes very easy. Just look at the labels and you'll see how many of them there are. So this notion here, I mean, the fact there is a map from one set to the other that is injective and surjective, is what allows us to conclude in the finite case that they both were going to have the same cardinality, which is ultimately what we want to generalize without counting. So in the finite case, if we have a function that satisfies these properties, we can count, and we're going to see that they both have the same number of elements or they have the same cardinality. Since we cannot count in the infinite case, instead of counting points, what we're going to try to see is not determine, I mean, as some absolute number, but we're going to define a relation based on the on the notion where we can compare sets using functions from one set to the other. So if we have a bijective function, which is surjective, I mean, bijective means it is injective and surjective. If we have such a, if there is such an f going from A to B, we're in the finite case that allows us to conclude that A and B have had the same cardinality. Now we're going to do the same. So it's going to allow us to classify things without counting elements. So we're just going to have to produce an bijective map from one set to the other to say they both have the same, I mean, this is in quotes, same number of elements. And this is a notion that, as I said, as I insisted, doesn't rely on the ability to count elements, but it's a property that allows you to conclude that two sets would have the same number of elements in the finite case. So this is an extension um, of this notion of cardinality. So cardinality would just be uh, uh, a class of functions, also an equivalence relation. So the class of functions they are related by the fact that there's a bijection from one to the other. That's an equivalence relation. You should try to do that. This is a good exercise. But once you define cardinality according to equivalence classes, you see that the equivalence classes, I mean, just extends this notion, because you can define here the class of all the sets of number of elements, and for finite sets have say 5, and in fact that will determine the same equivalence class. So you define the equivalence class of the number of of the sets such that their cardinality is equal to 5. You're going to find that those sets are the same class when you look at the classes from the perspective of there being or not of a bijective function going from one set to the other. So if you have sets with 5 elements, you can be sure that you can find a function like this, I mean a bijective function that goes from one to the other. And so the two things give you the same thing. I mean the notion of classes given a relationship, the relationship being, I mean, there being or not a bijective function going from one set to the other, or that you can count the elements and give you the same number, are going to give you the same classes of sets in the finite case. And so therefore, this is what we're going to use to extend our notion of cardinality to infinite sets. And this is what we're going to do then in the next video, and we're going to go through the notion of correspondence, which is something I basically introduced right here to you. And yeah, I mean, this is what we're going to be doing next. And briefly, again, as I said, we're not going to stop too much on every detail. This is not the point of, I mean, the main point of the course. It's going to give you a rough idea, but then you can complete the rest on your own, and you're encouraged to do so. And if you're interested then in this, I mean, you can also ask me. I mean, to find more details about this, you can ask me during office hours. That's it. So we continue in the next video.